Swayam Prabha. Digital India. Educated India.
Study I'm going to use is really the experience, kind of from my personal experience of working on the Linux kernel. This was during the time it was evolving to become an enterprise OS. So at that time, Linux was used, more in smaller, hobbyist kind of environments. A little bit on supercomputing or HPC. It was beginning to start to get used. But then this whole range of time, I mean, from 2000 to 2008 was the time that I was working on the Linux kernel, and essentially Linux was trying to grow up to be an enterprise operating system. And pretty soon now, if you look at where Linux runs, you see it runs pretty much on most of the data centers, most of the large scale environments and enterprises. They run Linux as a primary operating system. It also runs on your Raspberry Pi and your Android phones, and on the small end devices. uh, so at that time when we started, we didn't really know it was going to be that way. We used to work on Linux. Mostly it was a matter of, it was primarily, it was, a lot of it was, we enjoyed working on it. It was fun to work on it. And as you can see here at the bottom, I have this picture from 2003. This was really a trip met for Linux Conf AU in Australia, and Linus Torvalds was also there on that trip. And this is a visit to the Canberra Zoo, where we had this. You remember the story of Linus and why we penguin is that mascot for Linux, is that you have this. Linus was bitten by a penguin at that Canberra Zoo, and so this was his trip back to that same zoo with his daughters. And you can see, you cannot really see the penguin out there, but that's what his daughter is trying to reach out to. So it seemed for us it was fun. It was, you enjoyed these deep intricate things that you were working with OSs and watching it develop. Uh, but many years later on, there was an article that was published about contributors to the Linux kernel, and that article was titled "The People who are writing the software that is quietly running the world." And today, I think that is the case, that everything in IT, a lot of the major things are running on top of Linux. And so, how did we get there? And that's very cool. That is very satisfying. And that means the lasting impact of the work you do. But at the same time, it's a huge responsibility, because when you're trying to run the world, you have to deal with a lot of diverse situations, and you have to constantly adapt. And that's what makes working on program execution environment so interesting, because you have to execute. Almost everything is running as a program today, and you have to deal with those vast needs. uh, so at that time, this is about a year and a half after this picture I have, was when the 2.6 Linux kernel came out. And I remember there was this announcement saying it's evolving faster than any other operating system in history, and that there's a huge amount of change. And that time, it was 6 million lines of code. So a question for all of you: do you know how big is the Linux kernel today? I mean, how many lines of code does it have now? A rough guess is okay.
15 million.
15 million. Okay. Any other? Okay. Uh, so okay. So let's. Anything else you were saying? Okay. So you were kind of 50% there, right? So it was. It is actually around 30 million lines of code now. Uh, but look at the way the lines of code has increased over the years. So this time frame that I have, really, where I was talking about that enterprise environments, actually Linux, do you know when we started having SMP support in the Linux kernel? Which kernel version? So SMP support actually started in the 2.2 Linux kernel version. And the time period that I was working on it, we were working on it, this phase I said, it was really from 2.4 to 2.6 and 3.0, which was the time frame period when all of this enterprise requirements is starting in. So actually it had started having SMP support very early on, but it was not very scalable. For example, it would work well on, because we had very smaller number of processors, there was a huge kernel lock. So a lot of the scalability issues were there. How do you deal with large uh, uh, large systems, large block devices? All of that was evolving during this time frame. And so I see even 2.4 kernel where was the time when Linux was getting supported in more demanding environments, but 2.6 kernel was really that turning point when Linux starting to really become an enterprise OS. And there were a lot of enterprise folks from different companies who were pitching in and contributing. And that was kind of the turning point there. Um, so, um, so what does it really require, right? When you want to say we want us to work on an enterprise environment, what is the shift that is required? What are the changes that are required? I think you already went through the HPC session, so you've looked at the kind of scale of you have for supercomputers, and you've seen those pictures of the supercomputers, and what the computing capacity is. If you look at, say, an enterprise storage system today, um, you know, you've talked about hard disks and SSDs and NVM during your session on Friday. If you look at enterprise storage array, it's just to comprehend how it looks like. Yeah, we have so you can actually look this up, and maybe you already have. It's not just that hard disk device, right? Or you have a controller with it. These are full-fledged systems. So, to just give an example, when I came to HPE 7 years back and started working on an enterprise storage array, it was a 3-part storage array. Nowadays there's the next generation of it, which is called Primera, and that had this was multiple nodes. Each of them have are SMP systems. They have a hardware ASIC as well. They form this huge cluster, and that's the storage array. So that's the powerful storage array, which will have they would have caches. They would have a battery backed cache, so that if there is one node is failing, the other node can actually take over and you can immediately recover. So you have these huge systems right there. So you have huge servers, and so you have these huge storage systems. You have advanced networking systems. So that is kind of one of the aspects of enterprise program execution to deal with. Um, so what are the other things? What do you think what does that imply for the OS? Give it a shot. Think through it.
Hardening is a big problem, right? How do you harden it?
Good point. Yes. What else? That's actually a very good point. So because you have big hardware, um, what does it mean for all the data structures inside the operating system?
What does big iron mean? Like, what is exactly big iron?
Yes, so I think so big iron means hardware which is huge, which has many different components, many sophisticated components. Um, so these are maybe costly, expensive, big ones which are very complex and have many resources. So like you have many processors, right? You have many disk drives because you really want to get that kind of bandwidth. Um, you have you have to have a very powerful networking system. Uh, so I think the basics you talked about maybe a little bit is the issue when it comes is how you scale, because now you're going to run these huge workloads also on these systems. You're going to run an enterprise database on this system. You're going to run many, imagine the data center, right, where all of our requests are going maybe to a cloud system. So there is a huge number of processes, applications. They are doing very demanding jobs. They're serving a lot of huge number of requests. So there is a bottleneck. I gave that hint of why, even though you had SMP in the Linux kernel early on, but there was there used to be this infamous big kernel lock. So anything you try to do in the kernel, you take this huge lock so that it will be safe, but then that limits the scalability, right? The minute you try to scale up beyond 2 4 processors, it would do really badly. So scalability, and that's both you talked about, it's both scale up, which is that single system scaling up, and scale out, which is really the whole cluster. And then you had the discussion about NUMA a little bit. Right? So now the systems, as you noticed, right, the architecture of the system is changing, because when you want to scale up, then the the memory, that's a little further away from that CPU will take longer to access. So you have to deal with those kinds of issues. And then likewise, you often think of a lot of the discussion has been you're thinking about compute itself and how you scale the compute. But as I was saying, that you also have the implications that you have these really evolved storage systems. And so you need techniques for advanced storage management to have that kind of scale, have that kind of reliability, hardening, as they pointed out. And it really impacts the whole design of the IO subsystem, the block IO subsystem, how file systems are architected. We used to have that ext2, ext3 file system, and then ext4 was when we had to really take a huge jump to address that scale, because if you have these huge files and file systems, then how do you really support that? And that's how it became an extent-based file system to really address those very large files. Asynchronous IO is another capability, because you want to have that ability that you're, especially for databases, when you're running these database workloads, then you really want to be able to run these IO requests in parallel, right, with your processing. And asynchronous IO gives you a model to do that, and that was one of the another major feature that came up during that time. And then we have, the whole area of reliability, availability, and serviceability. So it's not just, it's hardening it. And so if you're in an enterprise environment, so one of the differences between, I'd say, an HPC and enterprise environment is that you're running many different applications, and you're running possibly very huge mission critical applications. So these applications have to, people are relying on that, and even a slightest bit of downtime means a huge impact. So you need reliability, and you need availability. So that's why you try to have multiple components be ability to fail over from that. Or maybe if you're looking at the storage layer, you really don't want to lose any data at all. And then they will fail, and they will fail in certain ways, in unpredictable, complex ways. And so you need a way to service that, to, if there is some problem that happened, how quickly can I figure out, what problem happened? And so there are these features like, and the Linux didn't have it at that time, because, so I'm going to talk a little bit about those kinds of examples of the serviceability features and what it took to bring that into Linux. And you have hot plug support, you could have tracing, and things like crash dump. And then, this is going to be a lot more deep dive on this topic as Mohan and Raman talk about virtualization and containers. This going back to the same point, that now these environments would have to support many different users, or what you call many different tenants. And the tenants themselves would probably have many different users who are running their workloads on them. Each of them will be running many different applications. And so there is a need for elasticity of these environments. So you should be able to run less jobs. You should be able to run more jobs. It should be able to expand and contract the use of resources. You should be able to isolate different users so that they cannot mess things up for each other, and they should not have to have, everybody should not have to have a separate system to themselves. And so how you carve that system out, have the right level of isolation, but still have it be efficient. Um, and a lot of things at that time happened. For example, sieve groups, for example, that enables containers, and which is what Raman will talk about later on. That was also evolving at the same time during this time period, during the 2.6 kernel series. And then, of course, there is security and privacy. These are very important things in an enterprise environment. So there are many such requirements. There are more that maybe if you can suggest some more here. Anything that I missed here that comes to mind?
I might be completely wrong, but I guess commodity hardware and management is ruled out by when you mention the term big iron.
It may not be. The thing is, what happens is commodity is always shifting. So what we thought was, big iron soon becomes commodity. You know, you wouldn't have thought before that your cell phone will have, multiple processors, right? You so it is actually, in fact, there is a trend towards a lot of this. If you look at, say, hyperconverged storage, or you look at a lot of server, there are server based systems, but they are still not very specialized, because what happens is, if you have very specialized systems, it's always hard to maintain and keep up. And as architectures and as all of these are evolving very fast, it actually helps to build these systems out of many commodity components. And so there might be a lot of, they will probably be a lot of commodity hardware also, where this becomes applicable. So that's that constant shift that is actually happening there. But one thing that I was thinking, so if the minute you think of these huge data centers or enterprise environments, and I have constantly talked about huge, but enterprise doesn't necessarily always mean huge. It might mean that you have your servers, they could be mid-range enterprises. You could even have an edge device, right? You might have these factories and these environments, again, which need very, which have demanding requirements, which they are enterprises, but they may have devices which are close to these sensors, and you have edge computing systems out there. So even that's part of an enterprise. So another aspect here is, because you're running this lots and lots of these huge workloads and huge environments, there is an issue of power consumption. And so there is a lot of focus on how you do power optimization in that. So in summary, I think it's bigger, faster, has to be stronger, has to be safer, both security as well as isolation, and how long it can last, and it has to be lasting. So you're not running a job and then going away, because many of these applications are probably running for a long time. People have to be able to depend on it. So you want this, whatever you do, to really last for a while. It should be easier to upgrade these systems also, and things like that, without bringing things down. Okay, so so that's, it's talking about enterprise systems. So this is a picture from the 2004 Linux kernel summit. This was around that 2.6 kernel, just before the 2.6 kernel came out, and this was the time when a lot of enterprise features that I was working on ended up getting accepted into the mainline kernel. And so you can see the diversity of people here, but I want to stop here, and I want to use this analogy, because the goal of this session today is not, as I was saying, is not to go too much deep into details, but I'm hoping that you can come away with a certain perspective on how you can build these program execution environments, which can support something that's very vast and diverse. And so I like to use this analogy of Gulliver's Travels to explain this. Um, so do you, I mean, can anyone venture right now as to, why I'm using that Gulliver's Travels analogy here? I think I've given a few hints now. Okay, so before that, maybe just confirm that, so have you read Gulliver's Travels by Jonathan Swift? Or has anybody read that? And so you can relate to the example that I'm talking about.
Read it long ago.
Sorry?
Read it long ago, so not completely sure.
Okay. So the gist of it was there was this Gulliver, sailor called Gulliver, who was traveling, and he's gone to different places in his travels, right? So he first goes to this land which is call that the where they were very land of Lilliputians, which is a land of very, very small people, right? So they were really tiny people, right, compared to him, right? And so that part of this of the story was really about Gulliver felt very huge in comparison to them, right? They're very tiny individuals, and how their life was and how that comparison was. Um, and then his next trip, he went to a different land, which is called Brobdingnag. And there, this was the land of giants. They were very huge compared to him, and he was this tiny person compared to them. Right? Uh, and so so that's the story that he went there. And so there's a lot of stories about the incongruity, right? Because how do their worlds look like, how they are their cities built, and how does someone like Gulliver fit there? Okay. Um, so I think of it as as this trying to work on Linux being a big challenge of how do you build a single city where both Lilliputians and Brobdingnagians can live. Right? And you can imagine how difficult a challenge that is. So I'll give a few examples. So I'll talk about a little bit about the block IO design, right? Because that's kind of where I started out, and this analogy really applies there. And I was trying to give you those hints with the small block devices to these large ones, and then I'll talk about a few other of these. So I will talk about one example of a synchronization primitive called read copy updates. I don't know if that's been covered before, so do let me know if that's been covered before, but I'm going to really again convey some intuition about that primitive and why that became important in this time. I'll talk a little bit about this whole serviceability and reliability aspects, and how that developed and what the challenge was there. And this last one I will not get time to talk about today, but there is a very interesting, how the area of Linux asynchronous IO has evolved. There's a pretty interesting saga around that. You have direct IO, which is what databases urgently needed, and that went into the kernel very soon. But then there was a lot of things around how do you make every kind of IO, every kind of operation asynchronous, and there was a lot of different contributors, even Ingo Molnar, Zach Brown, Ben Lahaye, then Linus Torvalds himself, and quite a bit of the work I did. We tried a lot of different things, but finally this it really got settled very recently, which is in the new interface called which Jens Sagsbo has actually introduced in the Linux kernel. And a few months back, I think, or maybe early last year, was when Paul McKinney and Jens told me, okay, finally we got buffered AIO working. And we got a lot of the work that we did at that time. Now they're finally in the Linux kernel. So it's a pretty long journey in some of these respects. So back to this block IO subsystem redesign effort that happened. Um, so the way I got into this was I was new to working on the Linux kernel. I had worked on many operating systems at that time, but I was new to the Linux kernel. We were working on something called dynamic probes, which was a precursor to kprobes. I'll talk a little bit about that. But I had been working on file systems, filter file systems. So I was very intrigued by the developments that were happening at that time. And I was working with and I was discussing these in these IRC channels. There were a bunch of people from SGI and Stephen Tweedy and many folks who were trying to really say, how do we scale up this block IO subsystem to be suitable for enterprise needs? Right? And so they had come up with a structure. They said this current structure that we have for block IO is really small. It's good for small IO, but once you start to have these really sophisticated devices, and you should be able to really handle much larger requests. You should not be bottlenecked in the OS layer, and there's no need for the OS to do a lot of these things because the underlying, the sophisticated storage systems are doing that. So they came up with a design, they called it kernel KIO buff. And because I had worked with filter file systems at that time, I was very intrigued by, okay, if you have these KIO buffs, what happens when the IO completes? And I really want to intercept it and do some, operation on post-processing it. So that was just an idea that I had, and I was discussing that with on the channel. And Marcelo Tosati, who was a 17-year-old, Brazilian kernel developer. He was actually an expert in memory management systems. Imagine that, right? And next to him was sitting Rick Van Riel, who was a 23-year-old, who was, the kind of expert there. And so Marcelo said, you have this idea, why don't you go post it on the mainline, on the kernel mailing list? And so that's what I did. So I posted this mail, and you can see the title of that mail, and was, RFC kernel mechanism called compound event weight. It's not very significant. It was an over-design idea that I had. But I came back the next morning and found that I had started a flame war. There were tons of mails there, and people were shouting. Thankfully, they were shouting at each other. They weren't shouting at me. What I had proposed was kind of by this time immaterial. So the debate was, and that's why I call this the big iron versus little iron tussle. The debate was really, and you can see this kinds of emails were there, right? This example here. And I thought I was seeing like a major showdown in the kernel community, but then I realized that it is really, it's nothing like that. So what was really going on here, right? Was that, I had proposed this on top of KI above, but the debate was about that KI above structure. Um, so there was a really good reason why we needed to change the block IO subsystem to handle these larger IO requests. But what Linus was sort of saying, he was saying that, yes, but in the process, please do not trample in trying to address this Brobdingnagian needs. Effectively, that's what he meant. Please do not trample on this Lilliputians, right? Because anything that requires low latency, anything which is people are using floppy drives as well. So there are lots of places where the kernel needs to do the job for them. You don't want to have this big bloated structures. And so so that's really what the debate was about. So you have to go back a little bit and say, what's the essence of that debate? And so that was really the challenge, is how do you build a system that can address these really large IO subsystems, advanced storage systems, have these sophisticated direct IO needs, because you're saying that maybe the OS doesn't need to do, because maybe the applications are doing a lot of this work, because you have a very sophisticated database which is doing its own buffer pool management, and it doesn't want the kernel to do its caching for it. Or maybe there is a sophisticated system storage array which does not want the kernel to do IO scheduling for them, because they are doing it under the covers and they're doing it in a much better way. But then there are all of these other devices for which you do need to have that kind of, you need to have a good IO scheduler. You need to be able to deal with systems. If you're just dealing with huge IO, but you're not thinking of the latency requirements, you need to be able to complete that IO in parts and be able to, operate on that. So that was that huge challenge. And really Jens Axbo, and by the way, do you know why I call this a brave new block IO subsystem? I mean, what is brave about writing a block IO subsystem from scratch? What do you think is brave here? Say what's different from maybe writing a scheduler from scratch versus writing a block IO subsystem from scratch? So if your scheduler goes wrong, your kernel probably doesn't work well, or maybe even it crashes. Right? You can reboot it and then we're fine, right? But if a block IO subsystem or your storage system goes haywire, you lose your data. And not only is that the case, you have so many different kinds of block devices, right? You have so many devices that have already been written. So when you're writing a generic layer like that, and all of those device layers, right, all of them have to change. And anything goes wrong, you lose data. people will be really, really mad at you. Now, at that time, actually, this was good thing, but for the Linux kernel was we used to have that development. It used to be a development kernel versus a production kernel. So you know, nowadays it would be much harder to do this kind of surgery, like what Jens did, and all the discussions that we had. In fact, after this was when we started having those discussions on how the block IO subsystem should be redesigned, and how these structures really, how do you have that balance between these kinds of structures. And so it was possible to do it at that time because you could do that kind of major surgery. Nowadays, it would be more difficult. Uh, I'm not going to go deep into how that was done, but the key idea there was really to have this enhanced abstractions. Not try to have this, the problem is with the mid-layer approach is where you have, the kernel always interjecting into things and trying to do processing for users. So what was really happening was that you had these, if you had a huge request, the kernel was going and block IO layer was going and breaking that up into many small pieces and then sending each piece down to the device, and then again accumulating that back and then sending that back to the file system. Right? So there is a lot of overhead in breaking that up and then again, piecing these together, right? Because you don't need to do any of that if your underlying device is capable of handling that. On the other hand, many devices can't take that kind of, you need to break it up for them. So the idea was to have this really a nice architecture where you could have these helper routines for different drivers in different environments. You could have multiple pluggable IO schedulers, and which would be suitable. For example, I mean, the next generation of this work more recently was when NVMe came about, right? And that led to the introduction of the block IO multi-queue scheduler, right? That whole architecture that Jens came up with was in response to that technology change. And then there was also the notion that what used to happen was that the buffer IO in the file system and this block IO were very tightly coupled together, which made it very difficult to deal with. Maybe you have a different kind of a file system which has a different need, and you have a different block device which has a different need. So things like trying to address some of those things. So there are a lot of involved issues there. So if you're interested, you can go back and hopefully look at the block IO subsystem a little more closely and see if you can understand why and how that evolution happened. So Linux, so in summary, right? I mean, so just to introduce this problem, so what we are really seeing is Linux as a kernel, and this is a quiz question for you, right? How many hardware architectures are supported by the Linux kernel today? I'm not expecting you to answer that right now, but maybe you can go back and look at your kernel tree and just look at the architecture directory and see how many there are. There are huge number of architectures that it supports. It supports, as I said, it runs on a mainframe. When I was working VM, people were looking at ported Linux to the S390 mainframe subsystem. It works on supercomputers. It works on your small devices. So it's a huge number of architectures that are supported. You have hundreds of different device drivers, and I'll tell you that's become a problem when we were trying to do crash dump for Linux, because now you needed it to work with all of these devices, and then you have to support all of these environments, right? And so that introduces conflicting design goals, right? Because now you're trying to build a city that's not just Brownians and Lilliputians, but very many different kinds of needs, right? You want it to be, the kernel has to be simple and efficient, otherwise it's not going to survive for a long time, right? Because it has to be maintainable, right? At the same time, you wanted to address all these diverse needs. You can do some of that using config options, but there is a huge value, as you can see, to having a single kernel that is running everywhere, right? It's so easy for us who are running, if you're running applications on it, you have to run that for Linux and that's enough, right? Otherwise, if you have to port to many different OSs, many different interfaces, that would be a lot more challenging. So it's a very flexible environment. It has to scale up to high-end systems, or what I'm calling this big iron stuff. And then you have to scale down to this really tiny low-end systems. You have to support data center workloads where throughput is very important. You also need to support routers or real-time workloads where latency is very important. And so conventional approaches, even though I had worked on many operating systems before Linux, it was really different. I mean, I had not had an experience like this, where you had to any feature that we wanted. We were thinking that we're just borrowing a feature which is there and say, AIX or say HPUX or any of these, other operating systems, and just putting it in Linux. But it never was just putting in Linux, because you had to think through these diverse requirements. And so it had often, you had to go back and rethink that whole philosophy and design it from scratch. And so, and not only that, that new challenges will constantly emerge with time. Some things, some trade-off that you've made, you thought was reasonable. So NVMe and persistent memory is one example, right? Because the whole assumption was storage will be slow, and then suddenly you are in a situation where storage is suddenly in like the microseconds range, and then suddenly now it's going into in closer to hundreds of nanoseconds range. So the whole trade-off in that equations are changing. Right? We used to think of SMPs as few CPUs, but then you now have huge number of CPUs. Almost every system is an SMP. Right? And so you have to deal with all these changes, and so that's another challenge when you are designing program execution environments which will live for a long time, right? And which will handle many things at different ends of the spectrum, because new workloads will come, but old ones also don't go away, right? Because people have built on top of that. You can't just change everything in the world in one shot. And so that's the main challenge there, and that requires, and that's why it's tricky, but that's why it's exciting. So I'll give one example of this, from with synchronization primitive, right? And I call this having fun with ideas ahead of their time. And I'll come to why I say that. But a little bit, of a recap. I think you've done this session on synchronization primitives, and you've talked probably spin locks, and so I don't know how far you've looked at it. And I think you've also looked at cache coherence protocols and so on. Uh, but let's see, just think of why it's hard to scale to many CPUs, right? Is that when you are, say, when you're using a spin lock, what are you really doing? You're saying that if I have multiple things which are going to use that, in entering a critical section, during that time, you want to block out others from entering that critical section. Right? So let's say there are, in the CPUs, so what you see is that there is if an updater comes in here on CPU 3, so it has taken that spin lock, and then it is updating, and then after that it will release the spin lock. During this time, anyone who is reading or who has to enter that corresponding critical section has to wait, right? And so that is time bitting, but that is getting lost, right? Because that time the CPU is not doing anything. Right? So this is, I'm talking of spin locks, by the way. So I'm not talking of sleepable locks or semaphores here. So that is the time that you're waiting. So now the question is, if I was giving that example of that big kernel lock, so that is a problem with a huge kernel lock. So what you tend to do is you say, okay, let's make the critical section smaller. So let's have fine-grained locks so that you have a smaller critical section, many of them, so there is less contention. Right? So if less contention is there, you will not lose as much time, because other CPUs who are not really operating on that critical section can proceed. Or maybe you're just holding the lock for that duration for that particular critical section. So that's great. You can do that, but is there a downside of having fine-grained locks? I mean, if you have many locks, right, that you need to take. So imagine that you're trying to do an operation that will require you to take, now suddenly it requires you to take multiple locks. You have to take a lock on maybe on that hash queue head to be able to manipulate that. Then you have to take a lock on another piece to manipulate that. You take a lock on another piece to manipulate that. You're now taking locks, many different locks. And to do locking, you usually do an atomic instruction. So this is an example. This is just showing the cost of an atomic instruction that you have. And this is on an old CPU, and I thought it was okay because, I'm referring to, how these techniques actually evolved. But you can see that in this case, if you just were to do a, typical clock period or running a single instruction, the amount of time it takes to the amount of time it takes in the best case when you're doing a compare and swap, it's already 33x. So if you do a lock based on compare and swap, then your best case is like 71x slower. Right? And this is the best case when everything is in cache. So if the minute there is a cache miss, that increases. So you have a single cache miss, you have a cache miss on compare and swap, and then look what happens when you are off socket cache miss, then you have a compare and swap off socket. So this will hurt performance even when there is no contention, right? Because every time you're taking the lock and then acting on it and then releasing it, taking the lock, acting on something, releasing it. So and this is right, this doesn't scale when you have many different, when you have large number of CPUs. So you looked at these cache coherence protocols, and you looked at how this works, right? How you snoop on that and then make sure that things are are coherent. And cache coherence protocols are expensive, and which is why people are there are, maybe when Mohan talks about some of the memory driven systems, he'll talk about systems where you try to relax that constraint there. But the problem is, so basically, when you want to do an atomic increment, as you increase the number of CPUs and threads, this overhead keeps increasing. It's because you now are bouncing around across CPUs. So that was just for a single processor. Once you have multiple processors, that keeps increasing. So what you want, so now you can see that if I have a critical section of, you're not going to have a critical section of one cycle, but if you're doing a really fine-grained lock, then you are really having 73 CPUs. This was the best case locking, if you remember, right? You're having 73 CPUs to break even with a single CPU. And so once you start contending, it becomes worse. So what you really want is that you want a primitive that can be as close as possible. This is what the read copy primitive theoretically is trying to do, that at least for readers, because a lot of the times in the data structures you've seen read-write locks, but this is an advanced form of a reader-writer lock. It's an advanced usage environment where most of the time you're actually accessing the data structure. So can you make that as light as possible? And so this was the conflicting design goals here, right? You want this to scale up to high-end systems, want it to support data center workloads. So if you do coarse-grained locking, it works for low-end but does not scale. If you do fine-grained, it helps high-end but will now especially hurt it starts to hurt the low-end, because now you have, you are anyway locking things out, right? And then you are now increasing that lock acquisition cost. So now you want to really scale all the way, and you want to support all of these real-time workloads. So now you want to come up with these lock-free data structures. And I will talk about, even if you do this, you have new challenges because we did this. So there is an idea of deferred destruction or deferred locking principle that is there. So what was this primitive RCU? So the idea is that the reader will make a copy of that data and traverses that copy of the data while the new copy is concurrently being updated. And the old versions get reclaimed once the pre-existing readers are done. Right? So it is the lightest weight conceivable read-side primitive in theory, and I'm saying in theory, that you should have read, unlock, and lock and unlock doesn't do anything. And by the way, RCU emerged through, there's a lot of story I can talk on the last day about how RCU really came about. It didn't come about by trying to solve the scalability problem. It came about trying to really avoid having to have a lock call in the read path. But all this is nice, right? Now you must be wondering, right? If you have something like this, how in the world will you know? How does the updater know the reads are done, right? Because you're going to say, I'm going to reclaim that when readers are done. How do you know that? And that's the trick here, right? So what you do is you say that there are actually implicit indicators in the system. Right? So every time when you're in a kernel section, right? You've already done a context switch. You've done you've switched the privilege level to the kernel, right? And then you will come out of it. So between these context switches, or between while you're in that section, that's an implicit indicator, right? When I'm exiting a system call, or when I'm exiting, going a context switch, that's an implicit indicator that I have done whatever, at least for the kernel, I've done that reading that I've done. This is true, by the way, for a non-preemptible kernel. And so what classic RCU does is it disables preemption in the read side critical section. But then, you have all of these readers coming in. So there's an updater, you wait for a grace period, wait for all the CPUs in the system to have gone through this change. So then comfortably, okay, nobody else who had started using that is still using it. I can release this. right? So that's the key idea. And there's a lot more to it. So hopefully you can go back and look it up in depth. Um, so that's the idea. Now, of course, I said this already. I hinted at this. This is disabling preemption, right? So now what happens once you start having kernel preemption? So once preemptible kernel means even in the middle of the time you're in a kernel, in that code, you can get preempted, right? You can explicitly disable preemption, but then now you are sacrificing latency, right? Especially on a real-time system. So not only can the reader be preempted, it can potentially be rescheduled on a different CPU, right? So now if you're having this per CPU state to handle this, how do you do that? Sometimes grace periods can take too long in this case, right? And you still want to avoid atomic instructions and memory barriers, right? And which are also expensive. And so I'm not going to talk about the solution because it is a really complicated, it's a interesting story, intriguing story. You can take a look at that. But ideas to do this actually had originated way back in 2002. So this is what I was talking. I had a discussion with Paul McKinney about it because I was working on something where I really wanted that read side to be nothing, and I was trying to solve that problem. But even though I came up with that idea and I was brainstorming with him, he pointed out, okay, that's that's a cool idea, but who in the world cares about real-time response and SMP scalability, right? If you have a huge SMP, you don't really normally read real-time response. So do you really need preemption there? Do we need to solve this problem there? 4 years later, the things changed, right? There was this whole notion of enterprise real time, and even financial transactions. There's so many of these places where you really need very low latency, but you are running, as I said, everything is becoming an SMP today. So the ideas became applicable, and that's when actually you developed it. That's where preemptible RCU went in one form. In fact, there's a much simpler version of preemptible RCU now in the Linux kernel. And another thing that happened was when you do virtualization, when you have KVM, there's a variation of this called sleepable RCU, again, which has to deal with this interruption. And so that's kind of where the work went. So uh, so that was about this read copy update story. The next one, and maybe I might do it a little faster, is so this whole thing of another thing. So we talked about large block IO. We talked about scalability. This is another requirement which is for serviceability. In fact, this was I use this term penguin who hated doctors because at that time the Linux kernel didn't have things like crash dump or tracing, or even the kernel debugger was kind of outside the mainline kernel. So there was, if you ran into a problem into an enterprise environment, which is what we were seeing with, if you wanted, our customers wanted to use Linux in the enterprise environment, but if you didn't have a way to do this, right, how would you support that? And many Linux distributions also had seeing that same problem, but the community, everybody felt that this is adding too much bloat or extra stuff in the kernel, which is not really needed, right? I mean, debugging and figuring out when, why do you put things in that, for that? So it's like the analogy of, of really hating doctors. Right? But, if you look at it a little more deeply, to understand why people were, worried about the approaches, the real issue was people were worried about the approach that was being taken to implement that. So the challenge is, how do you have, say with crash dump, I'll take the example of crash dump first. How do you have a reliable and flexible crash dump mechanism which can support, like, as I was showing, this large number of devices, right? And be easy to maintain. So in enterprise environments, when we do an enterprise operating system, sometimes we would have, we have a limited, as you say, right? Instead of commodity hardware, we are dealing with a limited set of hardware that's there from a certain set of vendors. So what you could do is you could go and create these device drivers that have a hardened path for crash dump. So what is a crash dump really? It's really taking a snapshot of the whole memory and state of the system when the kernel actually dies, right? When there's a real problem in the kernel. You don't want that to happen, but that does happen sometimes. So if that happens, you want to remember whatever happened and you want to save that back. And to save that back, you go and save that to disk. But now imagine that your disk is driver has a problem, right? Or there is an issue there. Then you are on the path when things are already bad, you're making things worse on the way down. So one way to deal with it is to have this separate path in this device driver. That's a hardened path, which is meant just for crash dump. It's a safe path. But imagine trying to do that. And so that's where the specialized solution started saying, okay, let's do an IDE only mini dump, or let's do just debugging over the network on the specific network net console protocol. Ingo Molnar came up with that. Or maybe you have a firmware based dump, right, crash dump. But these are specialized solutions. They don't work in this general environment. So there was the take one, and the things we've spent a lot of time working on, and it was and what we tried to do was we went the other way around, like that modular approach that I talked about with Block.io. We said, okay, let's have things for all kind of variations, right? We should be able to deal with different kinds of devices. We should have a pluggable framework. Some people want the full kernel dump, some people want a partial kernel dump. Can we configure the target type, the dump type, and do all of this? And this was 5,000 lines of code just to capture a dump. 5,000 lines of code doesn't seem much, but imagine the large part of this code is on the way down when the kernel is in that bad shape. So really, that was the challenge. So you want a simple, minimalist solution, but not simplistic, right? If you try a pluggable architecture, it's flexible, but it becomes very complex, right? People tried many other ideas. And so with the 2004 kernel summit, the approach that I was talking about at that time, and several people were involved in thinking about that approach, is to take a transform perspective. So the idea was, what is the minimum self-sufficient code? What do we really need when you want to do a crash dump? All you're saying, I want to remember that state of that memory and the devices and everything was there, right? All of these things, right? Putting it out to a device, all of these are really not the main point there. The main point is, how do I remember that? And so at that time, there was this effort there's a project called, another feature in the kernel that was going in called kexec. That allowed you to do a soft reboot of the kernel. So while the kernel was live, you could go and do a soft reboot of the kernel without really going through a firmware boot. He said, since we have this mechanism, what if we could have another kernel, which is a safe kernel, loaded up somewhere there in a protected manner, and essentially soft reboot into that safe kernel, right? So if there's a dying kernel, you save that information in memory, and you you reboot into that safe kernel while preserving rest of the kernel memory. And then you come up with a new kernel. Now, again, if you come up with a new kernel and then you start writing drivers and writing all the code in the kernel to actually dump it, it's again too much code. So what he said was, why don't we just expose that old kernel's memory, that huge memory, as a proc/vm core file that GDB can interpret inline, right? And then, because it's a file, you can do CP on it, you can do SCP on that, and you can operate it on that from the new kernel. Now, I know I made it sound very simple, but obviously there is a lot of complexity in how from that dying kernel, you can get a reliable kernel boot, and then how you do all of this. But the idea here was, now we had a minimum base, right? You could have any kind of flexibility. Anybody who wants to dump towards different target, you want to dump, across a firewall, you want to dump part of the kernel, you can do all of that. And it was just barely 1,000 lines of code over kexec. Another thing that we had, which was this thing with this was with kernel. So I'm looking at the time now. It's 11 now. So okay, maybe should I talk a little bit about kpros? This is the last one, or do you have any questions at this point of time? Okay, so let me continue the story with kprobes. So kprobes is really, I mean, if you look at the kernel today, you will see, you can do perf kprobe, or you have a feature called eBPF, which lets you, trace, what's going on in the kernel. So the idea here was, this was actually originated from something that was way back. It was in a product called OS2 that had it. And then later on, you see in Solaris also, kind of in the parallel time frame that we were working on this, and Linux Solaris came up with ttrace. The idea was that as you have a live kernel, this was crash dump was really after the kernel has crashed. If you have a live kernel and then you want to be able to debug, know what's going on, you could insert traces. And so those are intrusive. You have to put lines of trace code inside the kernel. The idea was here that can I really put anything, breakpoint at any point in the kernel and see what happened, right? And put some probe code to be able to trace it. And so this was the whole, this feature existed in another OS, and we tried to bring it into Linux. And so there were many things to that. How do you actually, at the time of a breakpoint, can you run a particular handler? When you're running something in the kernel, you want it to be safe. So we had like a Java-like language that could interpreted language that could run these probe instructions. And then you had a high-level compiler to deal with that. So there's a lot of code in there. And it was like 6,000 lines of kernel code. Now, what you wanted really was that you wanted the challenge in Linux, you could see, right? You want something that will be supported across all architectures. You want this to be useful for kernel developers. They should be able to use it. You want support teams to be use it, and you want to able to have system administrators to use it. And they all have very different kinds of requirements. And so even though we posted this, I think the first batch of deep probes that I posted was sometime in in 2000, I think, was when we developed this and we posted this, and it took several years to get into the mainline kernel. And the problem was this, right? That again we were putting in a lot of code here, which nobody uses in the common case, right? So you use it only when something goes wrong. You want that to be useful by kernel developers themselves instead of only having to go through this large user space code to be able to use it. So 2003 or so is when Rusty Russell said, go back to the basics. We have solved a lot of the sophisticated problems. We talked about scalability. We did a lot of trickery in here. He said, pare it down to the minimum self-sufficient code, right? This is an interface that gives you a way to say, this is a place I want to probe, and this is a handler routine. Do that correctly in an SMP safe way, but don't worry about optimizations, about using percipue data and all. Have a minimum patch. And so that was a 550 lines of code patch. And the cool thing was that once we had that patch, we brought back a lot of those things after that, but it became the basis. So somebody went and said, okay, maybe I don't want all of this things on top. I want to build a probe. There was something called there's something called system tap, which was built on top of it. And then today we see eBPF is built on top of it. And this is interesting article, by the way. You can take a look at it at ustack.io, which is talking about combining these two things. Like eBPF is a feature that lets you really intercept any place in the kernel and specify. It's almost like a kernel virtual machine, right? The equivalent of what we were trying to do with this in-kernel language interpreter. It gives you that kind of environment here. So there is a nice article on saying how these two things they think will revolutionize how you. It's maybe a little bit of an overkill to say revolutionize, but a very interesting ideas of how you can really do more cool things with both AIO and using eBPF in combination. So really, the summary of this is just to the perspective that I have learned from this is if you want to build something that will really work for a large amount of environments, you have to really think very hard about what is that minimum core. And it's okay to throw away a lot of code and go back and do that, because you keep learning from that and avoid over designing. And but it is a pragmatic choice, right? There's sometimes when reuse doesn't make a lot of sense, like the ext3 to ext4, there was a new code base. Linux said, okay, don't try to clutter ext3 with both of these sides, have a separate base for ext4. Even though in terms of the file system format, we had to think of migration and how that could be, some things could be backward compatible. And this, really requires a jump. This is where it becomes very interesting. You need wisdom and creativity all the way through. So that's the summary of my talk. So Linux, I think, continues to advance in new spaces. It's a huge code base now compared to what it was when I was working on, and the code base is constantly changing. I think last 7 years, 50% of the code would have changed. So that's why it's very hard to keep up to date if you're not really into that. But these things of efficiency and elegance are central concerns that keeps the kernel fun to work with. At the same time, it can continue to quietly run the world. Let's see how long it does. And you can come up with ideas in very surprising ways and sometimes, very unlikely paths. And this is a quote. I love this because when I was doing my PhD in ISC, I did a part-time PhD in ISC after 14 years. This was after I worked on the Linux kernel. He came there and students asked him, what is the secret to great research? And so the Turing Award winner who says this, that you have to love your failures. You have to be open to keep failing and failing and failing. So I feel that there are more interesting lessons from my failures than from things that I've succeeded in. So thank you for that, and these are things for further reading.